This is a worksheet that goes with the scalar and vector lesson. There's a PowerPoint and a video of the PowerPoint of the lesson going through just what a scalar and vector is. So once you've done that lesson, here's a little practice to go with it. You'll find a download of this worksheet at holdensclass.com. Go ahead and get a pen going. So if you follow this link, I'm going to try to link it so you can click on the video. I might not be able to figure it out, so you could just copy it in if I don't figure it out. But you follow that and you'll find the worksheet. It's just going to be a Word document rather than what you'll see in this PowerPoint, so I have more room to work problems. First thing, describing scalar versus vectors. Remember, scalars, I can kind of represent that by a line because it only has a magnitude, which would be the length of it and then also the unit that whatever it goes with. Whereas vectors would have a magnitude as well, so it would look kind of the same, but usually we would draw them with an arrow because vectors, we're going to be saying, okay, he's physically going from here to there, ending at the arrow tip, starting at the base of the arrow. Or they're going at a velocity from here to there. But it's going to have some sort of direction as well as the magnitude, so a little bit more. So let's take a look at number one. Number one, you see that he's going 5 meters north. So you have your magnitude, the 5 meters, but you also have a direction, which makes this a vector. The bench was 5 meters long. Well, there's no direction here. You can't put a direction on the bench unless someone's walking across the bench. So therefore, as is, it would be a scalar. 2 bowls of nachos, that never has a direction. That would be a scalar. Distance, just in general, you should know distance is going to be a scalar. And when it comes down to distance, velocity, displacement, speed, I tell my students that what you normally probably would have used, like the words like distance and speed, would have been scalars, and the other ones that you don't really use as much, but you may have used, would be vectors. So when it comes down to velocity, velocity is going to be a vector because it would have to have a direction as well. Displacement is kind of like a distance, but it's the vector version of distance because it also is going to have a direction. So it would be a velocity. Sorry, I skipped a couple. Let's go ahead and just finish these 4 off, and then we'll go to the other ones. Speed is going to be a scalar, which is comparable to velocity, but speed doesn't have a direction, and that's why it's considered a scalar. So back to just the definitions. If it has a magnitude and direction, it is a vector. Let's go look at this one, 7. He walked 8 meters forward. Forward can be one of those generic, he's going forward. I know he's going from one place to another. I'm not just describing an overall distance. So therefore, we can consider this a vector. Concert took 2 hours. Time will never be anything other than a scalar. You can't put a direction on time. 60 meters in a straight line. A straight line, he's going in one direction. So therefore, I can consider that a kind of hidden vector. And then has only magnitude. That's the definition of a scalar. Scalars have only magnitude, but they don't have the direction. So that's how you do this section. Next, how many vectors are in a paragraph? So here you have to kind of walk through, read the whole paragraph, and determine, is it a vector or is it a scalar? So let's take a look. John walked 5 meters north. Okay, this one, I will underline each vector. I'm going to cross it. I'm going to underline everything, but I'll cross out the underlines that aren't vectors. Here you have north, so this one's good. So he went 5 meters north. Then he turned right and walked 8 meters forward. Well, he turned right. I kind of can already assume that that's going to be east and walked 8 more meters. Not really a great way to draw a vector. When you draw a vector, it should be comparable. So this is 5. I should have it almost twice the size, which would be 8. Just the proper way of doing physics, so you would ignore this little section that I drew. Arrow tip should end over there. Then he sat on a bench that was 5 meters long. 5 meters long is not going to be a vector, so we'll cross that out. So only the first 2 are underlined. And then the concert took 2 hours. Time will never be a vector. It has no sort of direction. It's just a magnitude. Magnitude being the 2 and the hours. The unit is the hours. And then during the concert, he ate 2 bowls of nachos. So he was really hungry and ate those 2 bowls, but that is not a vector either. When the concert was over, he stood up and turned right and proceeded 60 meters out the door. So I could assume that he's going in a straight line after he turned right, and I just circled that, but I should have underlined that, giving you 1, 2, and 3, so 3 vectors in this sentence. So it's this one right here, 5 meters north, 8 meters forward. and 60 meters out the door that were our vectors here. All the other ones were scalars. Okay, in the next problem, this is based on a picture. Let me describe the picture. And on the worksheet, I print them half and half so they get pretty small. To get from your house to the park would be 1.12 miles. That would be a distance. To get from the park to the library, it's 0.95 miles. So I'm not describing one way or the other. I'm just saying between the two is 0.95 miles. That would be a distance. To the library, from the library to the friend's house is 0.3 miles. For 3 miles, and that once again is just not displacement, it's a distance. It's just not describing anything. These are all scalars right now until I walk from one place physically to another place. So you walk, let's go ahead and listen to this. They're asking for distance traveled from when you walk from your home to the library and into the park. So you start here at your house, you walk past the park, you walk to the library, and at that point in time you turn and walk back to the park. You never, so we're not going to use this right here, you're never going to your friend's house, so we're not going to use that 0.43. All you do is you go and mathematically with distance, you just add them up. So add, just remember, if it's distance, you add them up. That's all you have to do. I went 1.12 miles on the way to the library just to get to the park, plus another 0.95 miles to get from the park to the library. And then I turned, but direction doesn't matter, so I'm just adding things up. Then I kept on walking, but I was going in the reverse direction, which doesn't matter because this is a scalar distance. Another 0.95 miles. And I end up with an answer when you calculate that of 3.02 miles. So that's what you do. You just add everything up because you're going all the way here, all the way back. How far did you totally walk? You get an odometer, you would have that number. Then when it comes down to displacement, I could do more. If I didn't have this picture, I would have to do more, but displacement's just saying from the start to where you ended off, which was the park, how far was it and in what direction. So I can look at this picture, I can already tell you it's 1.12 miles, and I would call this, you could call it right, which makes more English sense, but since it's telling you this is x, and I know this direction is plus positive x, I'm going to say this is in the plus x direction. But if I didn't have all the different directions and I physically, mathematically wanted to walk all the way through this, I would have said to the right, or the plus x direction is going to be a positive value, and I would have said when you were walking to the park, you just went a positive. So the positive is a placeholder for the right, or the plus x direction. Positive 1.12 miles. And I'm going to add that to the next vector where I'm still going right, so it's still going to be, or in the positive x direction, so it's still going to be a positive. I'm going to add that to 0.95 miles. And then I'm going to add it to another vector, but at this point in time, we are now going backwards. We're going to go back, or minus a 0.95 miles. And so after wasting all this time doing the math, but if I didn't have the picture, this might be the best way to do it, I end up realizing that this is the answer. It's going to end up being positive, and that positive has to be turned into a positive x direction, or I'll take right if I'm one grading your paper. But if you have a different teacher, they might take something else. So 1.12 miles in the positive x direction. Next one. Okay, so the golfer sinks the putt. This first putt was this whole thing. He went past the hole. So just so they can give you only two numbers and not like the overall first putt and overall second putt, they show it to you this way. But that first total putt was 10 plus the 2.5. So it's 12.5. And here it's talking about what is the distance traveled. So I'm going to add everything up. To get past the hole, it was 12.5, and then he came back and did another 0.25. To get to the hole, you want to have miles, or meters here. You should always have the unit on the answer. And the final answer would be 15 meters. So this total thing he did to get back into the hole was 12.5 plus 2.5, or 15 meters total. Now this one, a golfer sinks a ball in two putts. What's the displacement? So really what it is, from start to where it ended off, And right now, just by looking at it, you can tell that it's 10 meters, and I would say in a positive x direction, because it does say that this is the x direction. So I already know it's 10 meters in the positive x direction, but if I wanted to physically do it like I did before, plus 10 because it's going to the right, I'm going to add that to plus 2 because it's still the first putt. Plus 2, it's still going to the right. Sorry, I'm using a mouse instead of a pen. I can't find a good pen. And then I'm going to add that too, but now we're coming back. We're going minus 2.5. Here, the last little part, this is right here. This minus 2.5 is this part right here. The second putt goes back 2.5, and that pretty much negates these two, leaving you off with 10. And I have this there. It'd be 10 meters in the positive x direction, but right would be fine for your direction. Just remember, if it's a displacement, you're going to put down the direction. If you don't know the direction, you usually can say forward or backwards. Okay, 18 and 19. A car travels 500 meters east, followed by 200 meters west in 95 seconds. I'm going to draw this out. I draw origin dot to say this is where I'm starting. I draw a vector to represent 560 meters. We don't have nice clean pictures, but that's why in physics you should draw them. And then you always start the next direction. So we went 560 east and then 200 west. You always start the next direction at the end of the first direction. So we are now here, and we're going to go ahead and go 200 meters west. And I just drew the picture of the scenario. But here, the first one's saying, what's the total distance traveled? So I'm just going to add them up. 560 plus 200, and that is going to be 760. And you should have meters and not a direction, because there is no, you actually change directions throughout this. Okay, for the displacement though, I'm now only talking about what could I have done instead. If I wanted to not waste all that extra time, I would have started right here, and I would have went here. So for the displacement, it's describing this arrow right there, what I just drew. From start to finish, what direction are you going from start to finish? What's the magnitude? And so if you take that, you take 560. This is where you need to have a positive 560 because you went right 560. Plus, once again, I call it adding vectors because that's what it's really called, even though it could be a negative, minus 200. So it might not make sense for you to write it this way, but for my description, because I added the vectors even though one happened to be negative, this is the same as saying 560 minus 200, which would be 360. And then I have to have the unit, and I should have at this point in time still had the positive, and now you have to determine, okay, that positive stood for east. So drop the positive, it's 360 meters east. They're a little easier to read. 760 meters was the first answer, and 360 meters east was the second answer. Okay, here, all we're doing is we're taking these values we got from before, and we're going to use V equals D over T. I'm going to simplify it. I know in class, I showed you what was in your books and on your equation sheet was change in X over T. The X is going to be the displacement. So if I'm trying to calculate speed, I'm going to use distance as my X. And I think on the equation sheet it actually has change in time too, even though we don't usually say that. We don't say, if we say to 95 seconds, this is 95 minus 0 or just 95. So we're going to use this for speed. When we're dealing with speed, we're going to say V equals, the displacement was, and let's look back at our last one, 760 meters. We're going to take the distance because we're calculating speed, and we're going to go ahead and divide that by 95. Whereas for the bottom one, I'm going to kind of do both of these at once. For the bottom one, we take our 300, we're doing the same equation, V equals D over T, or same thing, change in X over T. But in this case, we need our displacement here because we're calculating the velocity. But before they were asking for speed. So our displacement was physically 360. Since I'm not doing anything else, and for the sake of things, I'm just going to go ahead and write 360 meters east. That was our actual displacement. And that took 95 seconds. I just want you to see here, our unit is coming from this. And our direction is coming from that. So if you take 360 meters per second or 360 over 95, you get this answer when you type it in the calculator. 3.789 meters per second east. That came from that. And I kind of skipped the answer to the last one, but the last one before that should have been a cool 8 meters per second. So hopefully this helps with your basics. And if you're in my class, always feel free to drop me a line, ask me a little bit more. Have a good one. Bye.